Okay, let's talk about something fundamental. What if the very existence of particles, why some stick around forever and others disappear in a blink, isn't about some complicated property, but just geometry? Today, we're diving into a really cool new theory that could completely change how we think about the basic building blocks of our universe.
You know, it's one of those questions in physics that's so simple it's almost maddening. Why do some particles, like the ones that make up you and me, last forever, while others that are almost identical just vanish in a split second? It's a huge puzzle at the very core of reality, and we're going to look at a brand new idea that might just have the answer.
All right, to really get our heads around this, we've got to focus on a tale of two particles. They're super close relatives in the subatomic world, the electron and the muon. So check this out. The electron and the muon, they're almost identical twins. They've got the exact same charge, the same spin, they're in the same family of particles. But, and this is a huge but, the muon is over 200 times heavier, and because of that, it's wildly unstable. It poofs out of existence in microseconds. Meanwhile, the electron, it's basically immortal. So, what's the deal? Why the huge difference?
So, the theory we're digging into today says the answer isn't just, oh, it's more massive. It's something way deeper than that. The secret ingredient, believe it or not, is space itself. And I'm not talking about empty space, but the actual, literal fabric of reality.
Okay, so here's the central idea. It's called volume of space for shape. Now that sounds a little dense, I know, but stick with me. Picture reality as this giant, stretchy, elastic fabric. To make a particle, you have to grab a chunk of that fabric and mold it into a specific shape. That chunk, that volume you used, is what gives the particle its mass and all its properties. Think of it like a particle's spatial footprint, how much of reality's fabric it takes to create it.
And this gets us to the core principle of the whole theory, and it's so beautifully simple. The bigger a particle's spatial footprint is, the more of that reality fabric you have to bunch up to create it, the less stable it's going to be. It kind of makes sense, right? Imagine you're stretching a rubber sheet. The more you stretch it to make a shape, the more tension there is, and the more it wants to snap back to its original state. This theory is basically saying particles work the exact same way. Now, this isn't just some wild guess. It's actually built on 4 really solid logical steps. First, the theory says a particle's properties, its charge, its spin, everything, is its geometric shape. Simple enough. Second, it follows that similar particles, like our electron and muon, have to have similar or congruent shapes. Okay, makes sense. Third, where do these shapes come from? Well, they're built out of that fabric of reality. And that brings us to the fourth and most important point. Scale is everything. The more fabric you use to make the shape, the more mass you get. And, crucially, the less stable the whole thing becomes.
Okay, so let's take this new geometric idea and apply it directly to our original mystery, the electron versus the muon.
When you look at it this way, things really start to click into place. Their stability, totally opposite. But their basic shapes are congruent. They're the same, which is why they have the same charge and spin. But the real kicker is that space representation. The electron, it's made from just a tiny little pinch of that reality fabric. The muon, on the other hand, needs a much bigger chunk. And according to this whole idea, that one single difference is the entire reason it's so unstable.
Yeah, there's a quote from the source material that just nails it. It says, "The muon is much more unstable because the volume of space of the fabric of reality that is needed to construct the muon shape is much larger, even though the shapes of electron and muon are congruent. So, bigger spatial footprint, same shape, more unstable." That's the whole idea in a nutshell.
Now, a really good theory doesn't just explain one little thing in isolation. It has to connect with what we already know to be true. So the big question is, how does this geometric idea mesh with one of the most famous, most bedrock principles in all of physics?
I am, of course, talking about Heisenberg's uncertainty principle. Now, for what we're talking about today, it basically describes this fundamental trade-off. Put simply, the math shows that particles with more energy, or mass, tend to have shorter lifetimes. It's a cornerstone of quantum mechanics, a rule of the universe.
So here's where it gets really interesting. How do these two ideas fit together? Well, Heisenberg's principle is this incredibly powerful mathematical rule. It describes the relationship between mass and lifetime perfectly. But you know what it doesn't do? It doesn't tell us why that relationship exists. And that's where this new geometric theory comes in. It's not trying to replace Heisenberg, it's trying to give it a physical cause. I love this analogy. Think of Heisenberg's principle as a law that says taller, heavier sandcastles collapse faster. It's a perfect description of what happens. This new theory is the kid on the beach explaining why. Well, yeah, because a taller sandcastle needs way more sand, it's way more delicate, and it's just inherently less stable when the next wave comes along. One is the what, the other is the why.
So stepping back, what's the big picture here? What we might be looking at is a major shift in how we see the universe, moving away from just describing things with math equations and toward understanding the actual physical geometric machinery that makes it all tick.
All right, so let's boil this all down. What should you really take away from this? First, a particle's stability might just be determined by how much space, how much of reality's fabric it takes to make it. Second, that creates a simple trade-off. Use more of that fabric, and you get more mass, but you get less stability. Third, this isn't just a cool thought experiment. It offers a real, physical reason behind the math of Heisenberg's uncertainty principle. And finally, it even gives us a new way to think about how energy bends space-time. Maybe it's not just bending it, but actively shaping it to begin with.
And that leaves us with one last massive question to chew on. We've just talked about the electron and the muon, but what if this isn't just about them? What if this is a universal rule? Could the whole entire particle zoo, all the wild and wonderful particles we've ever found, all be explained by a secret, elegant language of pure geometry? Not just math, but actual shapes in the fabric of reality. It's a pretty mind-bending thought, isn't it?